Welcome to the course Structural Analysis. I am Dr.S.Pachaiappan, Assistant Professor, Department of Civil Engineering, Aditya University. So today is a 22nd lecture. We are going to discuss the ILD for shear force. So far we have discussed what is the concept of ILD and also how to compute the reaction force RA, RB by using the concept of ILD for both the point load and then the UDL. We know how to calculate the reaction forces. So in this lecture, we are going to see how to compute the shear force by using the concept of ILD. So at the end of the lecture, student can able to apply the concept of ILD for calculation of shear force. So I have taken the simply supported beam. You can say it is having two supports A and B, and then we have one unit force 1 which is located x distance from the support A. Now what I am going to do, I am going to calculate the value of RA, RB. So in the previous lecture itself, we have seen for the simply supported beam, one unit force is acting on the span. What is the reaction force? We already computed. RA is nothing but L minus X by L and RB is X by L. It's very simple. RB means this value X divided by L and RA means this distance L minus X by L. Okay. Now I am going to calculate the shear force at the point C. You consider point C is exactly at the L by 2 distance at center, which is separated the linear distance. From the left support, the XX section is located at a distance of A. From the right support, the XX section is located at the distance of B. So span AC is the left portion and span BC is the right portion. So when the unit load is on the left portion, first case, this is case 1, you see, I have kept the unit load left portion. Left portion means what? Inside the, from in between the support A and the XX section, I kept the unit force. Now what I am going to do? I am going to calculate the shear force at the point C. So shear force means what? In between the support A and XX, whatever the forces acting vertically upward direction, whatever the forces acting vertically downward direction, I am going to sum up. Okay. So what are the forces are acting? RA is going in upward direction and then the one unit force is coming in a downward direction. So RA plus RA and one unit force is minus 1. RA is nothing but we have the value of L minus X by L. So minus of 1. I am multiplying this L and minus 1. So L minus X minus L by L. Okay. So L will be get cancelled. I am getting the minus of X by L. So when I am putting X is equal to A, X is equal to A means what? This load I am considering exactly acting at the XX section. If you put X is equal to A, what it means? The load 1 unit or 1 unit force is acting exactly at the XX section. So if you replace it, I am getting the shear force at the point C is nothing but minus A by L. So we got the shear force at the point C is minus A by L. In similar way, what I am going to do, now this time I am going to keep the 1 unit force at the right direction. Right direction means what? Keeping the 1 unit force in between the section XX and then RB. Okay. So reaction force not going to change. RA and then RB we have the value. Now I am going to calculate the shear force at the point C. So you see from in between the A to my XX section only RA is there. Only we have a RA. In between here to this XX distance no other loads are there. So the shear force at the point C is now RA alone. So shear force at C is equal to RA I have taken, and then instead of L minus X I am substituting the value B, because this is nothing but our L minus X. Okay. The distance between the C and B is nothing but L minus X, and also we can see that say that is a B also. B is equal to nothing but L minus X. Okay. So instead of L minus X, I put the value B. So shear force at B is nothing but B by L. Now I am going to construct the shear force diagram, ILD diagram for shear force. So horizontal line, here it is 0, here also 0, and then The positive value at the point C is B by L, we are calculated, and then the negative point is A by L, we are calculated here. So at point C, we have a two shear force, one is minus A by L, another one is plus B by L. So this is the diagram ILD for shear force. Now, by using this ILD for shear force, how to calculate the shear force of the real beam? Let's see. I have taken the simply supported beam which is having three concentrated loads moving from left to right. The intensity of the load is 70 kilonewton, 60 kilonewton and then 50 kilonewton. Okay. So, how we calculated the reaction force in the previous lecture, in the same way we are going to calculate the shear force also. First, I need to draw the ILD for shear force diagram exactly below the given problem or given beam. Now, I need to drop the ordinate for the loads. See, 70 kilonewton I have drawn in the ILD diagram, and then I need to drop the ordinate for 60 kilonewton. I need to draw the ordinate for the 50 kilonewton as well. And exactly I need to keep the center of the ILD diagram to the point C where we are going to calculate the shear force. Okay. So, by using the similar triangle principle already we are discussed, I am going to consider for example, how to compute the x1. x1 can be easily calculated by using, for example, we calculated the B by L. So, you see here A is equal to 6 meter and then B is equal to 6 meter, because we are going to calculate the shear force exactly at the center. So, in ILD diagram we have two values, one is B by L and then minus of A by L. So, that was calculated here. This is the B by L is 0.5, A by L is 0.5. So, what is the B by L? This 6 meters by total length of the span is 12 meters. Okay. A by L, A is 6 meters, total length of the span is 12 meters. So, 0.5 we calculated. So, we put 0.5 divided by 6. This is for the larger triangle. 0.5 I am highlighting here. So, the larger triangle ordinate is 0.5 divided by 6 meters equal to then x1. x1 divided by the smaller triangle span is 4 meters. Okay. So, this is where we substituted here. We got the value of x1 is equal to 1 by 3. In similar way, I am going to calculate the value of x2 and then value of x3. Okay. By using a similar triangle concept, I calculated. Now, the shear force at the point C, point load means what? Load multiplied by ordinate, that's it, right? So, 70 kilonewton load multiplied by the corresponding ordinate, what is the x3? The value of x3 is 1 by 6. So, 70 multiplied by 1 by 6. Now, you have observed that I put minus 1 by 6. Why? Because you see the x3 is in the negative ordinate. Negative ordinate means we need to substitute the value minus, symbol minus, or if it is a positive means we have to put the positive value. Since it is a negative ordinate x3, I am using minus of 1 by 6. And then the second load plus 60 multiplied by corresponding ordinate. Corresponding ordinate is x2. x2 is nothing but, the value of x2 is nothing but 5 by 12, and this is also the negative ordinate. So, minus of 5 by 12. Okay. We need to consider the 50 kilonewton load also. So, 70 multiplied by the corresponding ordinate, 60 multiplied by the corresponding ordinate, 50 also can be considered, but this is the positive ordinate. Okay. So, 50 and then corresponding ordinate here is x1. You see the value of x1 here. x1 is 1 by 3. It is 1 by 3 we are substituted. So, we have two negative ordinates. x3 is negative, x2 is negative, x1 is positive. That is what we are substituted here. So, it is very simple. Whatever the beam is given, in the below that we need to draw the ILD for shear force diagram, drop the ordinate exactly for the load, draw the similar triangle, compute the ordinates, load multiplied by ordinate plus next load multiplied by ordinate plus next load multiplied by ordinate going to give the shear force diagram, the maximum shear force value. So, by this way we can able to calculate for the UDL also. UDL means what? exactly under the UDL, first I need to drop the ordinate like this. Okay, I have dropped the ordinate. This is exactly under the UDL. Now, after dropping the ordinate, I need to highlight that portion, and then I need to calculate the x1, x2, x3 values and all, wherever the load is there. For example, here the point load is there, and here where our UDL is acting. So, UDL portion is highlighted here, shaded portion. Then I need to calculate the value of A by L and then B by L. So, A is nothing but 4 meters. You see A is 4 meters here, and B is 3 meters. Sorry, A is 3 meters, this is 3 meters, and this is 4 meters. So, exactly we are going to calculate the shear force 3 meters from the left support and then 4 meters from the right support. Ordinates are dropped. Now, compared to the earlier case and this case, what is the difference? If it is a concentrated load, load multiplied by the ILD ordinate, that's it. But if it is a UDL, load multiplied by the area of the shaded portion in the ILD diagram. Let's see that one. We calculated the value of x1 by similar triangle. We calculated the value of x2 by similar triangle. We calculated the value of x3 by similar triangle. Okay, all these values are calculated. Let's see how it is come. For example, x1 you see the larger triangle is 4 meter length. So, x1 is this small triangle which is 2 meters. Okay. So, x1 by 2 for a larger triangle is this value B by L. B by L is a 4 by 7 divided by the overall span is 4. So, the larger triangle is nothing but B by L by 4. B by L is nothing but 4 by 7 by 4. These are for larger triangle. And here we can see smaller triangle is 2 meters and then another smaller triangle is 3 meters. In the negative ordinate, we have one x3 value. For this, the larger triangle is 3 by 7, which is A by L by 3. Okay, this is a larger triangle equal to smaller triangle is x3 by 1. So, this is the smaller triangle which I am marking here. Okay, by using a similar triangle, we computed the ordinates. Now, what I have to do? You see, the 80 kilonewton per meter multiplied by the corresponding shaded portion. This is one trapezoidal and then we have the another trapezoidal. So, A plus B which is x3 and then A by L, A plus B by 2 into H. So, H is 2 meters. So, this is this diagram. Okay. So, this is this diagram. The UDL is acting 2 meters here. I am marking here it is acting 2 meters. So, this is 2 plus 80. Once again, because I am going for this smaller portion which is ordinate 4 by 7 plus 3 by 7. This is A plus B by 2 into 1. So, this 1 is this diagram. So, totally we have a 2 trapezoidal. This is for the first trapezoidal. Okay, and this is for the second trapezoidal. And this is for the point load. 90 multiplied by the corresponding ordinate x1, the x1 is 2 by 7. So, it is very simple. If it is a point load, then point load multiplied by the corresponding ordinate. If it is a UDL, that UDL multiplied by shaded area of the ILD diagram under the UDL, area of the ILD diagram under the UDL. So, in that case, we can able to calculate the shear force. So, in summary, what we have learned? We learned how to calculate the shear force of the simply supported beam by using the concept of ILD. Okay, so in the next lecture, we will see how to calculate the bending moment using the concept of ILD. Thank you for watching this lecture. Thank you.